So in the last period, we have studied about the entropy. Entropy is the measurement of the disorderedness or randomness or chaos in the system. We have seen that entropy depends upon heat, that is Q, and if and entropy is inversely proportional to the temperature. So if temperature is higher and heat, same amount of heat is absorbed, the disorderedness created is less. But if entropy is if the same amount of heat Q is absorbed at a lower temperature, it creates more disorderedness, and ultimately we write that delta S is equal to Q reversible divided by T. And then we have started solving some of the problems, and we have seen that when a liquid crystallizes into the solid, the entropy decreases. Then, my dear students, when the temperature of crystalline solid is raised from 0 Kelvin to 115 Kelvin, the particles start moving around their mean position, and that is why the entropy increases. Now we want to study about the entropy change into the chemical reactions. To understand the entropy change into the chemical reactions, I have suggested that if suppose you have a reaction that is A mole of A plus B mole of B, that gives C mole of C plus D mole of D. Suppose this is your chemical reaction. So in that case, you uh, you this A and B are the stoichiometric coefficients of reactants, and C and D are the stoichiometric coefficients of products. So you write that delta N gas is equal to Np minus Nr. You just need to calculate the delta N gas for the chemical reactions. So Np is equal to D plus C and Nr is equal to A plus B, my dear students, and ultimately by doing that you get a delta N gas. Here in this particular case, if you look at this, Np is equal to 2 because you have 2 moles of gas, 1 mole of CO2 and 1 mole of H2O, but here Nr is equal to 0 because there is no gaseous moles available, and that is why delta N gas here is actually 2. That is Np minus Nr, that is 2 minus 0. So my dear students, we have a simple rule that if delta N gas is increasing, that is if it is greater than 0, entropy increases. If delta N gas is less than 0, entropy decreases. And if delta N gas is equal to 0, we need to think about the another reactants and products other than the gas, and and that is why on the basis of that we can take the decision. So if the gaseous molecules are involved in this kind of chemical reactions, by calculating the delta N gas we can easily find out the result. Here in the given question, Np is equal to 1 plus 1, that is 2, Nr is equal to 0, and that is why delta N gas is equal to Np minus Nr, that is 2 minus 0 is equal to, and that is why we have delta N gas is positive, and that is why the entropy increases in these reactions. Now there may be the another explanation we can give, but this is the better method I find to calculate the whether there will be a change in there will be an increase or decrease in entropy. Here reactant is NaHCO3 solid and it has low entropy. Among the products there are one solid and two gases. So this is the another kind of explanation, and therefore the products represents the condition of higher entropy. So this is how we can say that entropy has been increased in this case, but that is what we explain with the help of the verbal explanation. We do not have numbers. Then we have the next question, which is hydrogen gas is hydrogen gas is converted to hydrogen atoms. So here we have molecules and here we have atoms. Once again, both are in the gaseous form. So delta N gas we can find out number of moles of gas in product is 2. You can see here number of moles of gas in reactant is 1. So Np is 2 and Nr is 1, and that is why delta N gas is equal to 2 minus 1, which is 1, which is greater than 0. Delta N gas is positive, and that is why the entropy increases. The another explanation we can give here is that Here one molecule gives two atoms, that is number of particles increases and leading to more disordered state of the system. And as the molecule is converted to atoms, more disorderedness is created. 2 moles of H atom have higher entropy than 1 mole of hydrogen molecule, and thus the entropy here even increases. Now my dear students, when milk is converted to curd, we just keep milk and that is converted to curd overnight sometime. So entropy decreases as the liquid turns to solid or semi-solid. Please remember. Then suppose when egg is boiled, generally what happens? We consider that as the temperature increases, entropy increases. But here the case is exactly opposite. Here if you give temperature, if you boil the egg, when egg is boiled, it liquid turns to be solid and thus actually entropy decreases instead of increasing when the temperature is being increased. So these are the few cases on the basis of which you can understand the change in entropy well, and I hope my dear students you understood it well. If you have any question you can ask. बच्चों अगर आपको कुछ पूछना है तो आप पूछ सकते हैं. Well, thank you for at least you reply whether do you have any question or you don't really have. Dear students, do you have any question? You don't really have any question.
We don't
No,
have any
sir.
question.
No, sir, no doubt.
So nice of you to reply. Thank you, dear students. Let's move forward. Now we'll look at the next question. For oxidation of iron, that is Fe solid plus 3O2, it gives Fe2O3 solid. Entropy change is for oxidation of entropy change is minus 549 kilojoule per mole. Just have a look to this. Minus 549.4 joule per Kelvin per mole at 298 Kelvin. In spite of negative entropy change of this reaction, why is the reaction spontaneous? Delta RH, that is the enthalpy, standard enthalpy of reaction for this reaction is minus 1648 multiplied by 10 to the power 3 joule per mole. So this reaction, as it has got entropy decreased, during this reaction, my dear students, entropy is being decreased because the solid iron absorbs the oxygen gas and turns into a solid substance. So entropy actually decreases, but still the reaction is spontaneous and spontaneous. What is the reason that this reaction is spontaneous? So let us understand. One decides its spontaneity of a reaction by considering delta S total. And we know that delta S total is equal to delta S system plus this delta S surrounding. So for calculating this delta S surrounding, here we want to calculate the delta S surrounding because delta S system has already been given to us. To calculate delta S surrounding at temperature 298 Kelvin and where the delta system is minus 549.4 kilojoule per mole, and when the delta H reaction is minus 1648 kilojoule per mole. So by using this data, we need to calculate the delta S surrounding for this system. So to calculate delta S surrounding, we need to consider heat absorbed by the surrounding, which is equal to minus delta RH. So this delta RH we will have to convert into the negative form. We consider at temperature T, here T is already given. So entropy change for the surrounding is delta surrounding into minus delta RH divided by T, and T is 298 Kelvin. So it is minus into minus 1648 because we just need to convert it into minus. Multiplied by 10 to the power 3 joule per mole divided by 298. That is one. That is uh, 16,48,000 divided by 298, and thus we get 5,530 joule per Kelvin per mole. The positive value of entropy of surrounding that shows that the entropy of the surrounding is increasing. So as the entropy of system decreases, entropy of surrounding increases. Now we know that delta S total is equal to delta S system plus delta S surrounding. So let us put the value of delta S system. Delta S surrounding is 5530, whereas delta S system is minus 549.4 joule per Kelvin, and finally we get 4.98 kilojoule per mole of the total change into the entropy, and ultimately during all this process the enthalpy or total entropy increases, and as this total entropy increases we can say that the reaction is spontaneous. So my dear students, we determine the overall entropy change by calculating the total change in entropy, that is delta S total, and when we calculate the delta S total, my dear students, we get the idea about whether the entropy has been increasing or decreasing during the reactions. Uh, my dear students, now we want to study about a new thermodynamic function, that is what it is known as the Gibbs energy. Let's have a look to the Gibbs energy, dear students. We have been trying to understand the factors that determine or affect the spontaneity of the reactions. These factors may be: number one, it is temperature, it is entropy, it is enthalpy. We have seen in the most of the general cases, increase in entropy, decrease in temperature, and decrease in enthalpy or exothermic reaction, that is release in heat, are the general observation for the change in the direction of that leads to the spontaneous reactions. So up till now, whatever we have discussed, we have seen that entropy depends upon temperature, spontaneity depends upon temperature, spontaneity depends upon entropy, spontaneity depends upon enthalpy. We have observed that when the temperature increases, entropy increases. These are the observations. We did not come to any conclusion. When entropy increases, spontaneity increases, and when we have seen that when the energy is released, that means if the reaction is exothermic, we have found that this kind of reactions are generally spontaneous. But now we want to come to a conclusion, and we want to derive the relationship between the factors of spontaneity and how the spontaneity can increase or decrease. So now we want to come to conclusion. So we are discussing these things. But what happens? But any one factor alone cannot determine if the reaction is spontaneous or not. So from any one factors like temperature, entropy, and enthalpy, we cannot determine whether the given reaction is spontaneous or not. We generally find out that the cumulative effect of all these three determines the spontaneity. So if we want to determine the spontaneity of a particular reactions, we will have to consider these three factors. So why don't we create, or why don't we find out some relation among these three factors, and we can cumulatively understand whether the given reaction is spontaneous or not. So let us try doing this. We have seen that some delta S is equal to negative, delta H is equal to positive, and delta T is equal to negative reactions are even spontaneous. That means some reactions where entropy decreases, they are endothermic, and if the temperature even decreases, they also behave spontaneously. So why this happens that such reactions are even spontaneous? It is the cumulative effect of all this that lead to the determined spontaneity of the reaction. We can see it as if all these three factors, that is enthalpy, entropy, and temperature, must be there in some relation with each other. The relation among these three factors is defined as the new thermodynamic function. So my dear students, the relation between these three factors, entropy, enthalpy, and temperature, this relationship is known as the new thermodynamic function, which is known as the Gibbs energy function. So the relation between the entropy, enthalpy, and temperature is the new thermodynamic function, and the new thermodynamic function is Gibbs free energy, or Gibbs function, or Gibbs energy functions. So let us understand Gibbs energy, which is denoted by G. Gibbs energy G is a new thermodynamic function that is the relation between the three factors affecting spontaneity. Let us establish the relation among them. Let us look at that about G and its definition and understanding. Gibbs energy is also called Gibbs function. Gibbs energy is denoted by G. Mathematical formula to represent Gibbs energy G is equal to H minus Ts. Gibbs function is a state function. Please remember, it is a new thermodynamic function and it is a state function. What does it means? It means that Gibbs function depends upon the initial and the final state of the system, but does not depend upon the pathway, how the system is brought about from initial state to the final state. The change in the Gibbs energy for the system, that is delta G system, can be written as delta G system is equal to delta H system minus T delta H system minus S delta C system. You know that G is equal to H minus Ts. Now if you put delta both the side, what do we understand? That delta G is equal to delta H minus Ts. That means we can write it easily here that is equal to delta H, and one time it is T delta S and second time it is S delta T. Now my dear students, we understand usually the subscript system, actually this system subscript I am talking about, the subscript system or sys is dropped out and we can write delta G is equal to delta H minus T delta H minus S delta T. Now my dear students, for constant temperature, you know, we suppose if delta T is equal to 0. So that is what it shows, the temperature is constant. Therefore, delta T is equal to 0. That means the isothermal change, and that is why S delta T is equal to 0. Now you can see that this term S delta T becomes 0. So finally what we get is delta H is equal to delta H minus T delta S. So as my dear students, this S delta T is equal to 0. We can write that delta G is equal to delta H minus T delta S. Someone has got their mic on, please. Anurag, I think it's you. Okay, so this is how we get delta G is equal to delta H minus T delta S. How do we write this in the words? We can write it as Gibbs energy change, that is delta G is equal to enthalpy change, that is delta H minus temperature, that is T, multiplied by the entropy change delta S. So my dear students, the Gibbs energy change equal to the enthalpy change minus temperature multiplied by the entropy change. Equation delta G is equal to delta H minus T delta S is known as the Gibbs equation. So sometime in the exam, if you are asked write the Gibbs equation, you can write this delta H minus T delta S. Delta G is equal to delta H minus T delta S. It is your Gibbs equation. Gibbs equation is one of the most important equation in the chemistry, because using this Gibbs equation we come to know or we get lots of information, and it is useful in many industrial processes that you will study in 10th standard. Here we have considered both the terms together for the spontaneity, which both the terms, enthalpy and entropy. So my dear students, here we are taking the account of both the terms enthalpy and entropy simultaneously in the Gibbs free energy system. Energy in terms of delta H and the entropy in terms of delta S, which is a measure of disorderedness or randomness of the system. So these are the factors affecting the spontaneity. Now, if we look at the unit of G, my dear students, dimensionally, if we analyze, we find that the unit of delta G, that is Gibbs energy, is the unit of energy, because the terms that are related to delta G, they are enthalpy change and entropy change, that is delta H and delta S. And we know that the T delta S, that means Kelvin into Joule per Kelvin. So this Kelvin goes away and we can have Joule. Same way, delta H is measured in kilojoule per mole. So kilojoule per mole plus Joule per mole, or we can say that the ultimate unit that we get is Joule for this change in Gibbs energy, and that is why it has the unit of the energy. Now let's consider how delta G is related to the reaction spontaneity. That means how do we understand whether the given reaction is spontaneous or not by using this equation delta G is equal to delta H minus T delta S. Let us have a look to this. Delta S total is equal to delta S system plus delta S surrounding. If system is in the thermal equilibrium with the surrounding, then temperature of the surrounding is same as that of the system. So if system is in the thermal equilibrium with the surrounding, my dear students, the temperature of the surrounding is same as that of the system. So when both the system and surrounding are in equilibrium, they have same temperature. Also increase in enthalpy of the system. Also increase in enthalpy of the system, therefore entropy change of the surrounding will be delta S surrounding, that is delta H surrounding divided by T. That means delta S surrounding is equal to minus delta H system divided by T. Now my dear students, we want to study delta S total, that is delta S system plus delta S surrounding. We know that delta S total is equal to delta S system plus minus delta S system divided by T. Now let me explain this once again to you, my dear students, that suppose we have delta S total is equal to delta S system plus delta S surrounding. If the system is in equilibrium with in thermal equilibrium with the surrounding, then temperature of the surrounding is same as that of the system. Now what happens if enthalpy increases for the system? Remember that enthalpy delta H increases. So delta H increases means delta H is greater than 0, or we can say delta H is equal to positive. When delta H is equal to positive, what happens? The enthalpy of the system, or the system needs energy. The system needs energy. From where this energy comes from? This energy comes from surrounding. So if the enthalpy of the system increases, the enthalpy of the surrounding must decrease. So for surrounding, we have delta H is equal to minus. So that is why, my dear students, for surrounding, if you write delta H surrounding is equal to delta H by T, but then for if we instead of delta H surrounding, if you write delta H system, then this enthalpy, this energy which delta H system is required, that comes from the delta H surrounding, and that is why instead of delta H surrounding, we can write delta H system. But both have the same enthalpy, just the sign has to be changed. So delta H surrounding is equal to minus delta H system, and that is why instead of delta H surrounding, we have written minus delta H system. Now delta H surrounding is equal to, please remember that we have been calculating only delta H surrounding, but now we express delta H in the form of delta H system, not in the form of delta H surrounding, and that is why we put minus sign. Now now we have the equation delta S total is equal to delta S system plus delta S surrounding. For delta S surrounding, we can write this particular formula. So for delta S surrounding, we have written minus delta H system by T, and we already have delta S system here. So rearranging the above equation, we just write the equation once again, and then we come to know that T delta S total is equal to T delta S system minus delta S system. How is this? Suppose you have delta S total, that is equal to delta S system minus delta H system by T. So when you take T as a LCM and multiply all of these terms with T, suppose you multiply with this with T, this also you multiply with T, this even you multiply with D, these T and T's can be, and that is why finally you write T delta S total is equal to T delta S system. This T and this T can be removed, and we can write minus delta S system. So for spontaneity, my dear students, this delta S total must be greater than 0, and that is why T delta S system minus T delta S system minus delta H system should also be greater than 0. Now if we multiply both the sides with the minus, 0 multiplied by minus 1 is equal to 0. But all these terms, if we make it minus, what this minus turns plus, and that is why delta H system minus T delta H system, and this is what it is, the formula for delta G, and that is why delta minus delta G should be greater than 0. That means delta H minus T delta S should be less than 0, or we can say delta G must be less than 0. So this is the condition for a reaction to be spontaneous, my dear students. Once again, for reaction to be spontaneous, for spontaneous process, from all this calculation, we come to a conclusion that delta G must be less than 0. So when your delta H system, that is enthalpy change of the reaction, your T delta S system is the energy which is not available. So in this equation, delta S system is enthalpy change for a system. T delta S collectively is known as the energy which is not available to do the useful work. Please remember this term, that this term T delta S is collectively known as, this term T delta S is collectively known as the energy which is not available to do the useful work. So my dear students, here the term T delta S is known as the energy which is not available to do the useful work. That is what it is created due to the randomness of the system, and therefore delta G is equal to net energy available to do the work. So the total energy of the system is delta H system. Out of this energy, some energy is not available for doing some work, and finally delta G is the net energy available to do the useful work. This is how we understand the Gibbs energy function or change into the G. Thus, delta G is the measure of free energy. Please remember that this delta G is called the measure of free energy. That means the total net energy available to do a useful work. And that is why delta G is also known as the free energy. For this reason, it is also known as the free energy of the reaction. So this is the energy which can be utilized to do a useful work. Delta G gives a criteria for the spontaneity at constant pressure and temperature. So now using this delta G, we can come to a particular conclusion whether, or we can finally decide whether the given chemical reaction, when it is going to be spontaneous and when it is not going to be spontaneous. Now finally we can say if delta G is negative, the reaction is definitely going to be spontaneous. If delta G is positive, the reaction is definitely not going to be spontaneous. And if delta G is equal to 0, my dear students, we come to a conclusion that delta G is equal to absolutely 0. And when delta G is equal to 0, it represents the equilibrium state of the system. Please remember, my dear students, that we have studied that at equilibrium state, the enthalpy of the system is maximum. And therefore, delta G is equal to delta H minus T delta H, which is equal to 0 at, this is what we can write at equilibrium. So my dear students, at equilibrium we can write delta H is equal to T delta S. That means enthalpy change of the reaction is equal to energy which is not available for to do the useful work. We have already known that T delta S is known as the energy which is not available to do the useful work. Now an important note, if you please note it, if a reaction has positive enthalpy change, that is delta H is equal to greater than 0, it can be spontaneous when T delta S is less than 0, and thus T delta S is greater than delta H. That means delta G can be less than 0. And in such cases, those reactions which seems to be non-spontaneous, they also behave as a spontaneous reactions. So endothermic reaction can also be when delta H is positive. That means endothermic reaction T delta S must be negative, and thus T delta S is less than 0, delta S is less than 0, T delta S is greater than delta H. And if T delta H is greater than delta H, only if T delta S is greater than delta H, when T delta S can be greater than delta H, when delta S is, means change in entropy is big enough to overweigh the delta H, or delta S may be so small, but T is very high, so that T delta S can be greater than delta H. So my dear students, for T delta S to be greater than delta H, for a spontaneous reactions, delta S must be big, so there must be a huge change or huge increase in the entropy, or the temperature must be high. So these are the two conditions where the exothermic reactions uh, can also be made spontaneous, because your endothermic reactions can also be made spontaneous in this way. Thus endothermic reaction at very high temperature are spontaneous when, so endothermic reactions at very high temperature, they generally are spontaneous. So those reactions in which energy is needed, if you maintain a very high temperature for them, they are going to be the spontaneous reactions. Now, my dear students, we want to study about the comparative understanding of when delta G is going to be negative. So please understand, because in most of your exams, the questions are asked based on this equation, and the page number 112 is going to be very important for you. So when a reaction or a change is spontaneous or non-spontaneous, that is what we want to study here, my dear students. So we want to study when the reaction or when a change is going to be spontaneous. To study that, let us focus on the equation delta G is equal to delta H minus T delta S. Now let's look at the first scenario, what happens to this. So let's look at this. Suppose you have delta H is negative. So that is the exothermic reactions. And suppose you have delta S is positive. So this value, my dear students, delta G is equal to delta H minus T delta S. This value, if it is positive, so total T delta H is negative. Delta H is already given negative. This positive value for delta S makes overall T delta S negative. This become negative. This is already negative. So delta G will definitely be negative or spontaneous. So reaction is spontaneous when the delta S is positive. That means reaction is spontaneous when the reaction is exothermic. Reaction is spontaneous when the reaction is exothermic and entropy increases during these reactions. This was the first case. Now let's look at the next one. Let's have a look to this one. Here what happens, my dear students, you take the value of delta H positive. So delta H is already positive. Now your delta S is negative. But you have the total term minus T delta S. So this delta S, if it is negative, so it is minus T into negative. So overall, minus T delta S is positive. So this total term is positive. This term is also positive. So overall delta G is also going to be positive, and that is why the reaction turns out to be non-spontaneous. So this is how, my dear students, we understand the non-spontaneity. Let's move to the next case. These are the values for delta G. Here we have delta H. Here this is T, and this is what it is, delta S. Now what happens if we have the value of delta H is negative? So this term is negative. Now let's think about T delta S, which is minus. So when you have delta S is negative, so T delta S, your delta S is negative. This negative, this negative and negative may be positive. So what happens, your delta H is negative, but minus T delta S is positive. Now if this negative is greater than positive, then reaction is going to be spontaneous. Now when this negative is going to be greater than positive, that determined by the value of T. So if the value of T is small, if T has got smaller value, so when you have the temperature low, please understand, my dear students, if you have temperature low, in that case, reaction is spontaneous at low temperature. So my dear students, if the entropy decreases and if the reaction is exothermic, at low temperature it is going to be spontaneous, but if reaction is exothermic, entropy decreases, and if we have the higher temperature, then reaction is going to be non-spontaneous in this case, and this value of delta G will be positive, because this negative value of delta H and this negative this positive value of T delta S, this value is greater than this value because of the high temperature, and that is why the reaction become non-spontaneous. Now let's move and understand the next fact, that if you have delta G is equal to positive. So suppose you have positive delta G and you have, this is T, this is delta S, and your delta S is positive, your delta, sorry, this is your delta H, this is delta H, this is your delta G, this is T, and this is delta S. We have the relation this. Now if you have delta S is positive, that is why T delta S, which is minus, is going to be negative. And this value, if it is positive, what happens? If this positive value is greater than negative value, if positive value is greater than negative value, that means at low temperature, T has got the lower value. So when T has got the lower value, the reaction becomes non-spontaneous. So reaction is non-spontaneous at low temperature when you have the value of delta S is positive. Means if the entropy increases and reaction is endothermic, at low temperature it is going to be non-spontaneous, but at high temperature, if the entropy increases and reaction is endothermic, it is spontaneous. So in what cases, my dear students, we can easily understand in what cases a reaction is going to be spontaneous. Number one, when entropy increases in the exothermic reaction, it is always spontaneous. When entropy decreases in exothermic reaction and the reaction takes place at low temperature, it is spontaneous. When entropy increases in an endothermic reaction at high temperature, it is going to be spontaneous. Same way, my dear students, we can understand when a reaction is non-spontaneous. When a reaction is non-spontaneous, when entropy decreases in the endothermic reaction, it is non-spontaneous. When entropy decreases at high temperature in exothermic reaction, it is non-spontaneous. Entropy increases in endothermic reaction at low temperature. These are the three conditions under which the reaction is going to be non-spontaneous. So these are the six conditions we have studied using the Gibbs free energy equation. Temperature, low and high are the relative terms. For some reaction, the room temperature can also be the high temperature. So my dear students, please don't be so rigid by taking any decision regarding your question answer into the exam, that which temperature is higher and which temperature is lower. When you compare two reactions, for these two reactions, you generally compare the higher temperature and lower temperature. Generally, like on the base of the temperature value, we cannot determine whether the given temperature is higher temperature or lower temperature for a given reaction. So this is how, my dear students, we understand. So dear students, today we have introduced, let us revise the topic. Today we have introduced the new thermodynamic function. This new thermodynamic function was considered to be the Gibbs free energy or Gibbs energy.